Okay, all right. We will continue to our lab 3. Okay, in today's lab, we are design the control loop. First of all, we design the current control loop. Uh, you can first read all these things for a while. I'll give you 5 minutes to read all this thing, and then we start to design our control loop. All right, so to design the current control loop, we need to find the control transfer function. And to find the transfer function, we need to plot the body plot of our controller, which is this thing. And first of all, to plot a body plot in PSIM, we need a scan voltage, which is this thing, this sine wave. You just pull it out and don't need to change anything. And another thing is we need this AC switch. So just pull out these two things from your components and connect into this circuit as what I show here. And we also want to know the range of the wave frequency, which is what the range here. So we can calculate the range based on the document attached in this one. In this one, you can find it on your on the canvas. So I'll just pull it out here. The tau E and tau M is shown here. Use these two equations to calculate L divided on R. And you can calculate your own value. Mine is 1.3 millisecond. And tau M is J divided on half. My one is 12.28 seconds. And you put this like one on your tau E and one on your tau M is your FM and FE. So my FM is 13 millihertz and FE is 122.4. So first of all, everyone calculate your FM and FE and type your answer in your chat box to say, let me know you've already done this calculation. Yeah, the problem is for the tau E, the L is
the 0.92 is for motor itself, 2.8 is from the chopper.
The L is the total inductance, so it's 0.92 plus 2.8. TMJL, no. Those things are in your motor. So it's based on figure 3, DC motor parameter. So you can find your inertia, inductance, friction in your step 1. Okay, everyone should get the similar value with mine because we are using the same motor. So according to this lab notes, we should select our range of sweeping frequency 10 times larger which means we need to swipe like actually this one is not that important, but we need to swipe 10 times larger than of this value. So I choose to swipe from 0.01 to 1,000. So that's how we get the range. Okay, after you finish your simulation, you got this body plot, and by comparing this body plot with this one provided in your lab notes, you can find your omega-2 on something around here. So when you find your omega-2, you just fill in the blank here. The So you firstly rate the value you're rating is frequency. So the frequency is a value you find at the peak of your at the peak of here. For example, it can be from 40 to 90 hertz. It's really based on your observation, and also convert frequency to radians by and because you know what's the value of omega-2, you can calculate your time constant. To calculate your own time constant. This is how you get your omega-2 and time constant. Then we need to calculate our gain. So to find our gain, we first use this equation to get our omega-0. This equation to get our omega-0, which is 3,000, right? It's easy. Therefore, by convert radians into frequency, we have the F0 is 477.7 Hz. So this means at this frequency, we want the gain to be 0. And you find the point with 477 Hz in your body plot, which is here, and find your amplitude is around minus 13.5. So you put this value in here. This means the why we find this point is we want the gain at this point is 0. So that means we want a gain that can lift our this point 13.5 dB. So to calculate the Kp, what we do is we want lift 13.5, so it's 13.5, and dB is 20 log something, right? The that something is your Kp. So the Kp value is calculated from here. Okay, so that's how you calculate your Kp. The Kp is 4.7. Okay, so in this way, we finished the design of current control loop, but all this is only on the it's only calculation. To finish the PI controller, you need add on a PI controller here. So just pull out the PI controller and fill in the value you just calculated. This 4.7 is your Kp, and this time constant is your Ti. So don't use the same time constant with me because you all get your Ti based on your omega-2. So just fill in these two with your own value, and we finished the current control loop design. Okay, I'll give you 20 minutes to finish this design, and we will move on to speed control loop. Okay, I don't really understand your question. What do you mean by what's the chopper means?
Can you hear me?
Yes?
You know so in the diagram fig 7, you know how it says chopper in between the two summations?
Oh, this one. Oh, this is just a gain, so it's the everything same with this K. And this K is designed in Lost Lab. This K is already way designed in Lost Lab.
How do we, okay, how do we do that? As in, I know that we designed it last lab, but how do you, oh, wait a second, hold on.
Yeah, we're already building this block as like part of our chopper, which is part of our buck converter. So that's part of converter, nothing related to the controller.
Okay. How do you get the, I'm still a bit confused, but it's just a gain, right? Like,
Yeah, it's just a game. It's all based on Lost Lab, and let me see.
because I looked through the notes, it doesn't look like there's any, like,
It's
like,
the transfer function of the chopper. There's a times something, and that's the a is the k. So I'm trying to find where I calculate the a.
okay, is that, okay.
Oh, it is given in your lecture, in your lab note here. Yeah. So that's why the k. Yeah. So this G0 is this a. So it is already given you here is 2.4. You don't need to calculate that.
Cool, thank you, miss.
Okay, so I guess the confusing is from last time your B1 is 0.92 and Y this time is 3.72 is at the end of last time design, we add up inductor, right? We add up an inductance to smooth the current. So you not only need to add your inductor on the physical model, you also have to plus that value onto your mathematical model. So actually you need to update the A1 in your mathematical model. So it should be 0.98 plus 2.8. 92, sorry. All right, so let's continue to design our speed control loop. For speed control loop, we first need to find the KTAC, and this KTAC is because we want when the speed is 1500 rem, we want the V comes to be 5. So it's like a gain of these two values. So how to do that is 5 divided on, it should be just 115 as our last lab, but the value we use in this mathematical model is in radians. So we need to convert this 1500 to be radians rather than rem. So to convert this to be radians is times 2 pi divided on 60. In this way, you get the value of KTAC is 32 million. Then you can connect the KTAC on. So now you change this value to 32 amp and you run the simulation. And we're going to look at the speed and I guess is KRTV, RETV. Okay, so first we find when the speed go to steady state, it's around 722. It's around 722, and the because in your lab note it says the time constant tau is at 63% of full-scale output value. So the full-scale output value full speed is 722. So 63% is 455. And you find the value around 455. And you will find the time is around, the time constant is around 0.45, 0.4. So let me see. Okay, the time is around 128 milliseconds. So this value is 120 something, around this value, millisecond. And K is calculated by this value, by this equation. The maximum, the stable voltage of VRTV is 2.3. So here is 2.3 divided on 5, which is 4.6. All right, so now we got all the parameters we need to design the speed controller. So to design the speed controller, the datasheet we're using is this one, PI order 1. And the equation we are using is equation 2.3 and 2.4. So for the so let's first calculate the KB using this equation. So the tau is 120 something, or the value you read from your simulation, and TR is here, 100 milliseconds. So on my calculation, my KB is 6.68. And because we know KB, and A is, let me see, and our K is 4.6. So our A is using this equation. And our time constant is calculated by this equation. So mine is after you calculate all this value, you can add on another PI controller here to do our speed control. In our PSIM, it it is showing as this gain is our A calculated here, and the time constant is our TI calculated here. And you just connect back your speed loop, and by this way we finish our speed controller design. And according to your lab notes, you need to visualize the speed and the speed, okay, response time, everything. So that should be appear on your lab notes. So now we finished the controller design for our motor, and that's all I want you guys do in this lab. For part 3, you need to do it by yourself. I will not give you any guidance in this lab, so you need to finish part 3 by yourself, and that's it. So the left time is remain for yourself to do your lab, okay? Okay, I find a lot of students have a simulation error like Chen Peng. The problem is your 2K here. You need to flip it to another side. There's a like the error is go from here to here and from here to here. So make sure you do the right direction. Otherwise, you will have problem. All right. This is all about today's lab. For the lab report, you can only just answer the question of each question and put your simulation results inside this lab notes to make me easy to find out where is your result, where is your calculation, and also show me your parameter you put in the PI controller or the transfer function to help me uh, to find your problem or to find your error if you didn't really get the correct simulation result. So I guess this is all about today's lab. Hope you can work this out in this week. So we will see you next week. Okay, that's it.